Newton's understanding of gravity was good enough to allow us to fly from the Earth to the moon, but it's kind of got to make you laugh to think that you can go all the way to the moon and back using something that's ultimately just an approximation. It would make you chuckle to think that you could fly to the moon and back with just finite resources, yet Newton understood gravity well enough to be able to travel from Earth to the moon. Our world is flawless in every way. There are models everywhere on the globe, yet some riddles are still unanswered after years of study. What causes the one-way flow of time? What is reality? Why is gravity there? Why does traveling at the speed of light cause time to slow down? We have been interested in these questions for millennia. Imagine that I told you that gravity isn't real. It was entirely produced by the human mind. That may sound unbelievable, but that's what renowned physicist Brian Cox recently asserted. Let's examine the nature of gravity and the reasons behind the slowness of time. In realizing its detrimental consequences, we have to look beyond Newton. What he cannot accomplish is the issue, not what he understands. The fact that Newton's theory of gravity only makes predictions about an object's motion under its own force is one of its flaws. Neither the existence of gravity nor its mechanism is explained by it. Newton understood that it only forces you to count. The fact that it is only from Allah is crucial. It's really stated that the sun, planets, and comets, all of nature's most exquisite creations, only function in accordance with the laws and decrees of the wise. Put otherwise, I'll provide you with the means to comprehend how things work, but don't ask me how or why. That belongs to God. The enormous cosmos we live in is full of mysteries that we have yet to solve. Some amazing phenomena pertaining to time and gravity, two essential components of our existence, are included in this list of mysteries. Imagine living in a world where time is unusual, unpredictable, and the forces that keep us anchored are not the same. This is the point at which our knowledge of time and gravity diverges from Albert Einstein's theory of relativity. The renowned Albert Einstein, whose theory of relativity opened our eyes and changed the way we understood the universe, provided us with a new perspective. Our knowledge of how time functions in various contexts, especially when we move at great speeds, is based on his work. It all began when Einstein postulated two crucial theories at the beginning of the 20th century, special relativity and general relativity. After its publication in 1905, the theory of special relativity altered our perception of space and time. It essentially informs us that regardless of motion, all non-accelerating observers are subject to the same set of rules of physics. Along with the well-known idea that time slows down or speeds up depending on the context, the theory also introduced the idea of social interaction. The light clock is among the most effective theories to explain time dilation. Imagine objects traveling at an amazing rate, almost the speed of light, in a spacecraft. Two mirrors in the spacecraft reflect a light beam that is perpendicular to the direction of travel. Light bounces vertically to move in a straight line, as observed from a plane. On the other hand, things seem different to an outside observer who is not traveling with the aircraft. They follow the beam's route after seeing the fast-moving aircraft. The beam has to travel further to strike the mirror since the aircraft is in motion. The speed of light is always the same for all observers, according to the principles of physics. As a result, the beam should resemble a lengthy diagonal route. Things start to become intriguing now. Both observers, within and outside the aircraft, must experience the same amount of time for the beam to travel. The light takes longer to reach its destination, though, because of the lengthier travel to the outside viewer. Time dilation is the term Einstein used to describe the perceived time gap between two observers, the amount of time it takes for one observer to approach the stationary observer. Thus, in this instance, the time variance is based on what you do. These trials verified the societal impact, so this is more than just a notion. Particles in particle accelerators like the Large Hadron Collider can, for instance, travel at almost the speed of light. Researchers need to account for the effects of time dilation in order to perform precise measurements. A universe where time is limitless and may be stretched or compressed to the strength of one's will is made possible by special relativity. It causes us to re-evaluate how we normally think and realize how much bigger than our experience the cosmos is. Proposed in 1905, Einstein's theory of special relativity revolutionized our understanding of the universe's structure, particularly with regard to time and motion. The critical theory demonstrates that independent of velocity, all non-accelerating observers are subject to the same set of rules of physics. Let's look at the fundamentals of special relativity to have a better understanding of it. The idea that everyone experiences light traveling at the same speed, independent of velocity, is one of the cornerstones of special relativity. The speed at which light seems to travel is always the same, around 299,792,458 meters per second, regardless of your speed. This concept contradicts the common perception that motion causes us to move faster. It seems that the speed limit of the cosmos is equal to the speed of light. We think that events that happen at the same time do not happen for everyone at the same moment because of special relativity. From a different angle, what you witness happening simultaneously won't happen to someone else. If two occurrences are happening in distinct locations and you are moving toward them, this idea, which seems odd at first, contradicts how we think about time. Among the most significant and practical hypotheses is the one pertaining to time dilation. As you walk, time will either extend or slow down. As we discussed in the last section, in comparison to a stationary observer, time appears to pass more slowly while you move more quickly. The closer you go to the speed of light, the more noticeable this impact will be. Imagine you had two identical twins, one on Earth and the other traveling faster than light into space. The twin in space will be younger than their earthly sibling when they return. Real-time dilation is the cause of this phenomenon, which is sometimes referred to as the twin paradox. The constant speed of light is the cause of this discrepancy. The twin in space saw the ticking of the clock as usual as they made their way toward it in little steps. The twin's spacefaring clock, however, seemed to be slowing down to Earth observers as they moved around the globe. Length contraction is another effect of special relativity. To a stationary observer, an item moving at a fast speed appears shorter in the direction of motion. When objects approach the speed of light, this impact becomes more noticeable. At normal speeds, it is quite minor. One of physics' most well-known equations, E equals mc squared, is a direct result of special relativity. This formula demonstrates the interchangeability of mass and energy. This implies that energy and mass may be transformed into one another. Understanding this idea is crucial to comprehending how materials behave at high speeds and how energy is released during events like nuclear attacks. There is more to special relativity than meets the eye. There is information that is helpful. For instance, GPS systems depend on satellite signals being accurate, but the time dilation effect kicks in as the satellites approach us. Our navigation system will become less accurate if the impacts of special relativity are not factored into GPS computations. We are forced to reconsider how we conceive time and space by special relativity. It demonstrates how the cosmos functions in a way that defies modernity. Time is a relative term that is impacted by movement rather than an absolute one. Two significant concepts that have been validated by numerous tests are the speed of light and the link between mass and energy.